Welcome to the Botbuilders 2018 FLL project. Today, our mission is to propose a solution that we believe is one of the most significant problems to space travel: cosmic radiation. We will look at the current technologies that are being evolved to help this issue and propose our own theories as well. Today, we identify the most significant problem to space travel as cosmic radiation. We propose that without developing countermeasures to this identified problem, that all other problems posed to crew and spacecraft are of little consequence. We will examine the current situation in light of emerging technologies while providing our own multi-county measure solution. Is cosmic radiation the most significant problem to space travel? To us, the harmful effects of radiation on both humans and their aircraft are the most significant issues among the many that we have identified. The damage that cosmic rays cause when bombarding the brain can result in both cognitive and memory impairments. These can manifest in just a few months. Exposure to cosmic radiation can also lead to an increase in carcinogenesis and can affect the nervous and cardiovascular systems. In a simulated test with mice, the test results revealed significant impairments in both recognition memory and spatial memory. Here in Graph A, you can see the significant decrease in recognition memory, while Graph B can show the decrease in spatial memory. Cosmic radiation. What is it? Well, there are two types of radiation that compromise cosmic radiation. Firstly, solar particle events, or SPE, and galactic cosmic rays, or GCRs. GCRs are a constant stream of radiation originating from ancient supernovas comprised of both protons and ions, where the dosage is dangerous when accumulated over several months. This Crab Nebula is a supernova remnant in our Milky Way galaxy. There are three countermeasures that we are proposing to you today. Firstly, induced synthetic torpor, magnetic shielding, and nanomaterial. For our solution to work, we suggest that all three of these countermeasures are combined to reduce the effects of cosmic radiation. Magnetic shielding. Magnetic shielding is conducted by superconducting magnets and is useful as it is not as heavy as the current solutions that can weigh down a spacecraft. However, new materials are needed such as aramid fibers and titanium sheaths to limit the mass of these magnets. Prototypes of magnetic shielding so far have shown a 75% reduction to radiation exposure. The only other aspect of this solution that is in a developing stage is the energy required of the spacecraft to generate this magnetic shield. This schematic shows the pumpkin magnetic shield prototype that is currently in a development stage. Nanomaterial. Nanomaterial is being developed by Dr. Mohsin Rahmani at the Australian National University. This is a thin film that consists of a layer of dielectric nanoparticles that are spread so thin that they are just 0.0005 of a millimeter apart. With a change in temperature, the function of the new nanomaterial can either absorb, reflect, or emit light and radiation. This A material can be applied to any surface, including spacecrafts and spacesuits. Further research will be needed to bring this product to commercialization stage. This picture shows nanomaterial at work as it reflects light radiation of varying temperatures. IST, or induced synthetic torpor, is defined as creating hibernating type conditions induced in non-hibernating animals. It is achieved through the medical research of therapeutic hyperthermia and creating conditions for human stasis. IST reduces the metabolic activity of the body and provides animals with higher levels of resilience to stress. Experiments conducted using marmots and squirrels pre- and post-hibernation have shown that the effects of radiation exposure were mitigated by a radioprotective effect of hibernation. IST would also need to be accompanied by total parental nutrition, which is where a person is fed with nutrition fluids. Many benefits come with IST, including a reduce in the spacecraft's total energy production, potential to reduce radiation exposure, reduction in consumables needed for the trip, minimize psychological challenges for the crews, reduced pressurized volume needed for living quarters, reducing the need for ancillary crew accommodations such as food and entertainment areas. And another benefit is that the research and implementation will further help organ transplantation and critical care patients. These are some of the many benefits that come with IST. This is an artist's impression of the IST currently proposed for astronauts. Our theory is to combine all three of these solutions to create a more efficient and reliable solution that will reduce the radiation exposure and its effects on astronauts. We hope that you have enjoyed our presentation today and consider these possibilities for future space travel. Thank you.